Hello. So I want to show everybody how to do how to use a Hermite M file in Octave to create an interpolation polynomial. So let's go to share screen. And let's go ahead and open Octave. Now, I'm going to do two particular things here. And you're seeing something that was I tried and it then didn't record. So we'll just do it from scratch. Hermite. So we start Hermite. And let's say we'd like to do the function e to the x. So you type e to the x here, exp of x. Make sure you use quotes like so. Then make sure we do the derivative, which is pretty easy for e to the x. Now, as far as the number of data points, the very first example I'm going to do, I'm going to use the nodes x equals 0, x equal 1, x equal 2, and x equal 3. So that is going to be, our n will be 3 here. So that's x equals 0, x equal 1, x equal 2, and x equal 3. We output it to the screen and we get this output here. And the question is, well, what do you do with this? What do you do with these numbers here? I'm going to say, no, I don't want to evaluate it. So what do we do with these numbers? Well, if we go up here, what we find, and I've copied these exactly, the thing to remember is that the polynomial you get is always going to be the constant coefficient plus the coefficient of x minus the first node, plus the coefficient times x minus the first node squared, plus the coefficient times x minus the first node squared times x minus the second node, plus the coefficient times x minus the first node squared, x minus the second node squared, plus the coefficient times x minus the first node squared, x minus the second node squared, x minus the third node, times x minus the first node squared, x minus the second node squared, x minus the third node squared. And the very last one is coefficient here, x minus the first node squared, x minus the second node squared, x minus the third node squared, and then x minus the fourth node. Now notice the very last term stops at x minus the last node. It doesn't have the squared. So these are the coefficients for this polynomial. So that's the 1, that's a 1. This is 0.178 because this is 10 to the minus 1 here. This is 0.28171, that's that here. This here, 0.097, that's this. 0.023, that's this. 0.005, because that's a 10 to the minus 3 right there. And this is 0.0009 because that's 10 to the minus 4. So this is in fact the interpolating polynomial. Now to graph it, I know I did this on graphing in Octave. It's probably though just as easy to graph in Desmos because you can use cut and paste. So if you cut this polynomial, and you can't remember, Desmos is not going to like it to scroll. So let's just go down here. And let's go to Desmos. So you have y equals, and you have this part, but then you need the next part right there. So it's going to be plus all this. Because again, Desmos doesn't like the scrolling. So just do a cut and paste. That works very well. Save you some time. And there is your graph of your interpolating polynomial. Now, if you want to compare to see how it works, let's go to y equals e to the x. You see it works pretty darn well, for the nodes in question, right? So that works pretty well. Now, let's do a second one. And let's run Hermite again. And this time, what I'm going to do, I'm going to choose a different function here. So this function I'm going to choose is exp of sine of x. That's kind of an interesting function. It's not quite as boring. It's just e to the x. Now, let's go ahead and calculate the derivative. Well, remember, the derivative of e to the sine of x is the derivative of sine is cosine times exp of sine of x. Just make sure we get this. Yep, I'll make sure we get enough parentheses. Now, to make this a little bit more tractable, I'm only going to use, instead of going n equal 3, I'm only going to use n equal 2. This is going to be a smaller. And my first node, instead of starting at 0, I'm going to start at 1, 2, and 3. Output to screen. There we go. Now, what do these tell us? Well, let's go to this right here. Here, f of x is the e to the sine of x, and x0 was 1, x1 is 2, x2 is 3. So our polynomial will look like, it'll be some coefficient, a0 plus a1 times x minus 1, because that's the first node, plus a2, x minus 1 squared, plus a3, x minus 1 squared. Now we go to x minus 2, plus a4, x minus 1 squared, x minus 2 squared. Then we do our, here's our last one, x minus 1 squared, x minus 2 squared, and our last node is 3, and that only gets power 1. So now we copy our coefficients, and this is our program output. Here are Hermite outputs. There's going to be this. And it seems like I lost my cursor. So let's just move this down a little bit. So what do we really want? Well, I want to cut and paste because there's less room for error here. So let's copy that. And let's just do this. Now your a0 is just going to be it's just going to be this. So let's get rid of that. Replace it by the coefficient. a1. Let's get rid of that and replace it by the coefficient. Copy. Paste. Let's get rid of this and replace it by the coefficient. Notice that's I'm going to get rid of the plus 2 because that has a sign to it. And then this is going to be, oh, now we're at 0.01. So got to do 2 adjustments here. Okay, let's get rid of that. Cut and paste. But remember, this is 0.1. So let's move that over. This is, we got to move this over. So, I mean, this is 10 to the minus 1 also. So better put that parentheses back. And let's see here. Let's just take a look here. That's positive point. Okay, that's positive. So, but that's point. So we had to put a plus there because I erased a plus by mistake. And then this is another 10 to the minus 1 with a negative. And that goes where our last coefficient is. So adjust this, I'll get rid of the plus. Then I'll put my decimal here because it's 10 to the minus 1. And there you go. Okay. So there is our polynomial. Now to graph this polynomial, I'm going to use Desmos because it's probably a little easier, but so let's do it that way. Let's copy. Oh, I didn't want to do that. Let's just not get rid of it, but let's copy this. I don't know what the heck is going on here. God, this is just so sensitive. All right. And let's just do a new one. Okay, there's our polynomial. And then here's a function we're approximating, e to the sine x. Now you might say, well, how good is that? Well, if I restrict my x between their nodes, it's quite good, as you can see. See that? A perfect overlap with our polynomial, which is the one in purple. So that's how you can use Desmos for this. Now, if you'd rather use Octave, well, that's okay too. Let's go back to Octave. And we don't want to interpolate this, but now let's go ahead and plot this with Octave. Now, what you need to do if you want to plot this, in this case, our nodes run between 1 and 3. So let's use a variable x equals 1 colon 0.001. 0.01 will work fine. That just sets the variable there. Now, as far as the y, if I post this as is, there's going to be error messages. So in order to fix this, I have to make this in MATLAB style, or not MATLAB, Octave style. So I have to make this a multiplication. I have to make this a multiplication. And then in order for this to square, it's thinking it's doing matrix multiplication. So if you put a little dot before that, that turns it into scalar multiplication. I mean, scalar exponentiation. So you have to do that. Then you have to, okay, you have to turn this into exponentiation. Then you have to turn this, you have to do the dot there because you're multiplying two variables. So this has to be a product. This has to be a dot. This has to be a product. And this has to be a dot. And let's see, did I miss any multiplication so far? I don't think so. And then finally, this is just a number multiplied. Let's see here. Let's just expand this to make sure. Yeah, okay, that's fine. So I have to make sure this is a multiply. Have to make sure that this is a exponentiation. Has to be a multiply. And you don't need the dots when you're multiplying by a number. You need the dots when you're multiplying by, something with a variable. That has a variable, so we better do that. And then this is a variable, so I better do that. And then I'm going to put the semicolon because I don't want to read all the matrix stuff here. So that looks like we did it right. So now let's plot x, y. And we get the following. We get that. And then let's say y actual equals exp sine of x. Let's plot x, y actual. And let's see, hopefully this works okay. And we can see they sort of plot right on top of each other. So you can use the Octave plot like I just did, or you can use something like Desmos. It doesn't really matter. I think the Desmos graph is a little prettier. I think it's less fussy because you don't have to go through there and put in all the little dots. But upshot, these are just going to be the coefficients for the polynomial in this form. So that should conclude this, and thanks for watching.